Good morning, Chem 20s. Our new chapter we are going to start today is called Solutions. What we're going to look at for our lesson today, however, is going to be the characteristics of solutions, conductivity, as well as litmus paper tests. You will remember from previous studies that matter can be split into two categories. What we're going to do in this chapter is we're going to look, however, only at mixtures, a combination of two or more pure substances. Now, you should also remember that mixtures can be subset into two other categories: heterogeneous mixtures, otherwise known as mechanical mixtures, or homogeneous mixtures, otherwise known as solutions. To remember that these two pair together, remember the memory aid he, me. Heterogeneous, he always pairs with mechanical mixtures, me, as well as homogeneous, ho always pairs with solutions, so. So he, me, ho, so. In mixtures, we have two categories. Under mechanical mixtures, this is a mixture that has visible divisions or regions. This is where I look at my mixture and I can see the parts. A perfect example of this would be oil and water. Oil would be sitting on top, water I could easily pick out below. They do not mix. An example maybe from your household might be if you were to have, let's say, a tossed salad for supper. You easily could pick out the lettuce, the tomatoes, the cucumbers, maybe a little bit of green onion. On the other side of that, we have solutions. Solution is a mixture that has no visible parts, meaning it's going to look uniform like one item. An example from the lab would be copper 2 sulfate. It looks like one thing. It's a light blue liquid. However, we know it's made up of little blue crystal solids that we have dissolved in water. An example from your house that would be a solution that we know contains more than one part, but it looks like one thing, would be soda pop. If you read the back of a can of soda pop, you would see that there's quite an ingredient list there. There's water, there's sucrose, there's glucose, there's fructose, there's caffeine, there's aspartame, there's artificial coloring. But it's funny because when you pour it into a glass and you look at it, it looks like one item. You never go, oh my goodness, look at the caffeine over there. Or, oh my goodness, way over on the right hand side of the glass is so much sugar. It all appears as one item. Well, the other thing about a solution is that there's always quantities that have larger amounts and quantities that have smaller amounts. The quantity that is in the smallest amount is called the solute. The quantity in the largest amount is called the solvent. And I want to remind us that in a solution, you have to have at least one solute or one solvent. You can have more than one, like in soda pop, but minimum is one of each. So if you think of this example here, I have a solution with sugar cubes in it. And so in this example, my sugar cubes would be my solute. It's the substance that's going to dissolve. In this solution, I also have the other substance, and that is my solvent. The solvent, in this case, the water, is the substance that causes the dissolving. In any solution, you can have both substances being gases, both being liquids, both being solids, or a mixture of each. Let's look at some examples. So, one possible example of a solution would be solid dissolved in liquid. An example of this would be if I took a scoop of sugar and I stirred it into my coffee. Once the sugar dissolves, it's one substance, one solution. Another example could be a liquid dissolved in a liquid. An example of this would be alcohol dissolved in water, like possibly ice cubes. Or another example might be gas dissolved in a liquid. Again, let's go back to my soda pop. There's carbon dioxide gas dissolved in there. So when I open it, that's what gives my drink its fizz. Fourth example would possibly be a solid dissolved in another solid. So if I take zinc solid and copper solid and I heat it up really hot until they go to molten state, I can mix them together. And then when they solidify back to a solid, I now have a new solution, a new compound called brass. And this is things like tubas or trombones are made out of. And then another possible solution might be gas dissolved in gas. If we think of the air we breathe, we know the air has oxygen in it, but it also has nitrogen and argon and carbon dioxide. It's got lots of dissolved gases. When I look around, it all looks like one substance. Now, we tend to have called in previous studies water as the universal solvent. And the reason we have said that is because more substances dissolve in water than in any other substance. So we have a term for this. And you'll remember when we reviewed at the start of the semester how to use your solubility table, we had a state called aqueous. Aqueous indicates that a substance in a solution dissolves in water. So when I say, for example, NaCl aqueous, that means I have taken table salt, sodium chloride, and I have dissolved it into water to make a solution. Aqueous dictates water as my solvent. Now, what we're going to spend the rest of this lesson on is looking at the two qualitative tests we have for solutions. One is litmus paper, blue and red, and we've used that before. And the second one is conductivity, and we've used that before as well. So this should really be a review. Let's start by looking at litmus paper. When using litmus paper, we can test for an acid. Remember, acids are indicated by the presence of hydrogen ions. So we are starting with a positive cation. So acids are going to work like this. When we use red litmus paper is going to stay red in an acid. Blue litmus paper, however, like the picture down below, when I touch it into an acid, it's going to actually turn red. So acids is all about red. Red stays red, blue turns red. Both strong and weak acids are going to turn litmus paper red. And remember, to pick out an acid, all acids have a hydrogen ion. So either the hydrogen's at the beginning, because that's where we put cations, like HCl, hydrochloric acid, H2SO4, like sulfuric acid, or the hydrogen's attached at the end after a double vowel, like in acetic acid, or you would know it better as vinegar. CH3COOH. Instead of putting the cation at the beginning, we put it at the end to close off the double vowel. And we have looked at this rule before. Now, for litmus paper, we can also test for bases. Reminder that a base actually contains a hydroxide ion, an OH minus ion. Bases are all about blue. Base is blue, BB. Blue litmus paper will stay blue, but red litmus paper will turn blue, like in this picture example. I have a piece of red litmus paper. When I dip it into a base, it's going to turn blue. Again, like in acids, both strong and weak bases will turn blue in litmus with the litmus paper. Now, bases are actually, although they contain hydroxide ions, they're actually just a very specific type of ionic compound. So if we take a look, sodium hydroxide, because it contains a hydroxide, it's a base. Magnesium hydroxide, because it contains hydroxide, it's also a base. Both of these would turn blue with red litmus paper. The third item we can test with litmus paper is we can test neutral substances. Now, neutral substances occur if you're one of three things. One, you have an equal number of hydrogen ions and hydroxide ions. A perfect example of this would be water. Water has two hydrogen ions and one hydroxide. Water has one hydrogen ion and one hydroxide ion. So it has one of each, therefore it balances out. That means when I test with red litmus, red is going to stay red. When I test with blue litmus, blue is going to stay blue. No changes occur for neutral. This is also true for ionic and molecular compounds. So if I were to test it in sodium chloride solution or hydrogen peroxide solution, both of these would not change the litmus paper. They would both test as neutral. Well, the second test we're going to look at is the test for conductivity. So for conductivity, we're going to use a conductivity meter. Ideally, this is very, very simple. It could be just a battery with two electrodes coming off, hooked up into an LED light. If it conducts electricity, it would be considered an electrolyte. Electrolytes are compounds that conduct electricity when in solution. Now, we don't have to use a conductivity meter. We could also use an ohm meter. You might have some use or might have tried one of these out before, let's say down in automotives. However, the nice thing about a conductivity tester is, or by labeling something an electrolyte, is it indicates the presence of ions. That means that there are ions floating around. We're talking about soluble ionic compounds, compounds that break up into their ions, including acids and bases. All substances, soluble ionic acids and bases, will all break into ions, therefore will conduct electricity, and we can call them electrolytes. Weak acids, as well as strong acids, both conduct electricity. However, weak acids have a lower conductivity because they have way less hydrogen ions that will be released in solution. Now, the opposite of an electrolyte in a conductivity test would be if my conductivity tester, the light did not turn on. This is called a non-electrolyte, compounds that do not conduct electricity in solution. These compounds, when I drop them and stir them into solution, they do not produce ions. Therefore, there's nothing for the electricity to jump through in order to complete the circuit. Examples of this would be elements, insoluble ionic compounds. So when I look at the solubility table, these are the substances that would stay as solids, and molecular compounds, because molecular compounds do not break into ions. And we have some examples here. Well, what I would like us to do is, using that information, I have 5 beakers labeled A, B, C, D, and E. I would like us to use the knowledge we just gained and see if we can figure out something to do with which of these mystery beakers, A, B, C, D, and E, is HCl, H3H6O, NaOH, NaCl, and H2CO3. We seem to have lost the labels off all of these substances. So I'm going to grab myself a pen right here, where I'll grab green. And we're going to see if we can fill this guy in. So let's look around. Oh, no conductivity. Well, if I take a look at my list, the only thing that doesn't have conductivity are elements, and I do not have an element. Molecular compounds, so that is something that is contained of only nonmetals, nonmetal, 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 and that looks like it would be C3H6O. So this to me looks like it would be molecular, so I'm now going to knock it off my list. Anything else that's really easy? Ooh, so we have stays red, turns red. So this is going to be an acid. We know it's an acid. However, because it's got low conductivity, we know it's a weak acid. Where down below in D, stays red, turns red, it's also an acid, but because it has high conductivity, this is going to be a strong acid. In my acid chart, in my data booklet, on page number 8 and 9, there is a line on page 8 and 9. If you have an acid above the line, that's a strong acid. All the acids below the line are weak acids. So if I take a look here, HCl is above the line. It's a strong acid. So I know that mystery beaker D is HCl. It's an acid and it's strong, which means the other acid on the list is carbonic acid, H2, and it's below the line, so it's a weak acid. So we're going to knock it off. Now, I have low conductivity, high conductivity, but it says here, ooh, no change, no change. So this would be high conductivity. This would be NaCl, because without a change, I know it's ionic or molecular, and the only thing I have left is ionic. And last but not least, blue. Blue would be my base, so I'm looking for something with hydroxide. This is my base.